Your gut answer would probably send you to the outer edges of the solar system, toward worlds frozen in perpetual darkness. Maybe Titan, where liquid hydrocarbons rain from the sky and the surface is wrapped in an orange chemical haze straight out of a nightmare. Or Triton, so far from the sun that just getting there is already a survival manual in interplanetary travel. It takes nearly 5 years just to approach Neptune's orbit, and there's still no dedicated mission to its largest moon. What about the tiny moons of Mars? We've been trying to land a rover on them for decades, and nobody's pulled it off yet. Titan, Triton, Phobos. Great candidates, all of them. Hostile, complicated, and yet none of them actually wins this contest. Because the moon that piles up the most obstacles, the most environmental violence, and the most orbital sadism isn't out at the fringes of the solar system. It's much closer, and its name is Io. Io orbits Jupiter at about 262,000 miles from the planet, a distance that on a cosmic scale is basically the equivalent of sitting on a giant's knee. That closeness isn't just a fun fact, it's the root of almost every problem. Jupiter isn't just big, it's monstrously massive, more than twice the combined mass of every other planet in the solar system, with a gravitational well so deep it turns any trajectory into an exercise in extreme precision. To reach Io, you first have to survive entering the Jovian system, where the planet's gravity accelerates your spacecraft to dizzying speeds. Then you have to brake hard enough to avoid getting locked into the wrong orbit, or worse, plunging toward the planet. And finally, you have to sync up with Io itself, which isn't exactly sitting around waiting for you. It completes a full orbit around Jupiter in just over 42 hours, screaming along at more than 38,000 miles per hour. It's like trying to jump onto a moving train while you're already falling down the side of a mountain. The problem isn't just physical, it's about energy. Getting to Io requires an enormous amount of delta V, meaning the total velocity change the spacecraft has to be capable of executing. Just inserting into a Jovian orbit costs a lot. The Galileo probe, for example, needed an engine powerful enough to decelerate by nearly 1,350 miles per hour to be captured by Jupiter's gravity. Then, dropping down to Io's orbital altitude requires additional maneuvers. Io is the fifth innermost moon in the Jovian system, but it's not the first. Between it and Jupiter lie Metis, Adrastea, Amalthea, and Thebe, all much smaller but even closer to the planet. So the journey isn't a simple orbital insertion. It's a complicated dance involving multiple braking burns, trajectory corrections, and close passes by other moons that gravitationally nudge any planned orbit off course. In practice, any mission aiming to approach Io has to wrestle with orbital logistics that would give a seasoned aerospace engineer a headache. But let's say you're a stubborn and exceptionally talented engineer. Let's say you actually manage to slip your spacecraft into the right orbit. Now, the second nightmare kicks in, the gravitational torture that defines Io's existence. The moon is locked into an orbital resonance with Europa and Ganymede, called the Laplace resonance, after the French mathematician who described it in the early 19th century. Every time Io completes 4 orbits around Jupiter, Europa completes exactly 2 and Ganymede exactly 1. This perfect clockwork rhythm prevents Io's orbit from becoming circular, forcing it to remain slightly elliptical instead. The result is devastating. The distance from Jupiter keeps changing, and the planet squeezes and releases Io without ever letting up. Literally, Io gets deformed by nearly 330 feet with every single orbit, like a cosmic rubber ball being kneaded by an invisible giant. Just a moment, guys. Only 13% of subscribers know when we publish new videos. Make sure you subscribe and turn on the notification bell, because without it, you'll miss formats and documentaries you won't find anywhere else. That constant flexing generates heat through friction deep inside the moon, a process called tidal heating. On Earth, we see a gentle version of this in ocean tides, which rise and fall twice a day. On Io, it's an infernal machine with no off switch. The energy generated by this mechanism is estimated at around 100 trillion watts. To put that in perspective, it's more than all the heat produced by Earth's interior, and Earth is a planet 3 times Io's size. Io's interior is kept in a state of near permanent melt. The result? Io is the most volcanically active body in the entire solar system. not very active, the most active. Full stop. No competition. There are hundreds of identified volcanic centers on Io's surface, with at least half a dozen volcanoes erupting at any given moment. The most dramatic ones have mythological names that do justice to their violence. Pele, the massive volcano first spotted by Voyager 1 in 1979, shoots sulfur plumes up to 190 miles high. If you were standing on Io's surface watching Pele erupt, you'd be looking at a cosmic geyser nearly as tall as the moon's radius. Locate Patera is a silicate lava lake roughly 125 miles across, a glowing mirror that periodically renews itself as the solidified crust sinks and fresh lava wells up from below. And then there are the mountains. Io is dotted with over 100 peaks, some taller than Everest, pushed upward by the compression of the crust under the relentless tidal heating. New lava flows cover the surface on geologically rapid timescales. If you landed in a seemingly quiet spot, you'd have no guarantee it would stay that way for years, months, or maybe even weeks. And here comes the third level of the nightmare, the one that makes engineers break into a cold sweat: the radiation environment. Jupiter has the most powerful magnetosphere in the solar system, second only to the Sun itself, 20 times more intense than Earth's Van Allen belts and 1,000 times stronger than Saturn's. It's a magnetic bubble so enormous that its tail sometimes stretches all the way to Saturn's orbit. This magnetosphere traps electrons and ions at extremely high energies, accelerating them to a significant fraction of the speed of light. Io orbits right inside this invisible furnace, in the heart of the most intense zone. Radiation doses near its orbit reach 3,600 rem per day. That's 36 sieverts. For reference, a human being starts showing symptoms of radiation sickness at around 100 rem received over a short period. A dose of 400 rem in a short time is already lethal for half of all people exposed without medical treatment. On Io, you'd hit that threshold in just a few hours. The entire human body would be destroyed within a day. No appeal, no exceptions. But the story doesn't end there, because Io isn't just a passive victim of this radiative devastation. It's also one of the architects. The moon continuously erupts sulfur and sulfur dioxide into space. These materials are immediately ionized by Jupiter's magnetosphere and accelerated along magnetic field lines, forming a structure called the Io plasma torus, a massive invisible donut of sulfur and oxygen ions encircling Jupiter at Io's orbital altitude, with temperatures around 1.8 million degrees Fahrenheit. And there's more. Between Io and Jupiter flows an electric current called the Io flux tube, a colossal invisible wire carrying up to 5 million amperes between the moon and the planet, generating auroras visible at Jupiter's poles. Io is literally a cosmic electrical generator, a 100 terawatt generator. If someone figured out how to tap into it, they could power all of human civilization today with plenty to spare. For a spacecraft's electronics, all of this is slow but inevitable destruction. The Galileo probe, which orbited Jupiter between 1995 and 2003, felt it firsthand. Its systems suffered progressive damage from Jovian radiation, with degradation in the quality of its high-resolution images. And Galileo wasn't even attempting a landing. It was simply passing near Io during planned flybys, each one a calculated trade-off between the scientific value of the data collected and the risk of destroying the probe prematurely. A lander on Io would need to survive being permanently immersed in that particle hell for however long scientific operations required, with heavy lead shielding that adds mass, cost, and complexity to the mission in dizzying proportions. But let's say that problem gets solved too. You have a perfect trajectory. You have heavily shielded electronics. You have enough fuel. Now you have to deal with Io's surface, probably the least cooperative terrain you could find among the large moons of the solar system. The average temperature is around minus 200 degrees Fahrenheit, but that average is as misleading as averaging a sauna and an industrial freezer. Near lava lakes and active flows, temperatures can exceed 2,730 degrees Fahrenheit. Some telescope observations have recorded even higher peaks during particularly violent eruptions. That means cryogenic conditions and extreme volcanic heat coexist in the same landscape, sometimes separated by just a few hundred meters. The ground is covered in frozen sulfur and sulfur dioxide, materials that can behave in mechanically unpredictable ways under the weight of a lander. There are no liquid oceans to splash down gently into like on Titan. There's no relatively predictable icy crust like on Europa. There's a chaotic mosaic of young plains, lava flows, and volcanic deposits in constant evolution. There's also another subtle but crucial detail. Io has an extremely thin atmosphere, composed mainly of sulfur dioxide with traces of sulfur, sulfur monoxide, and a few ionized species. It's so rarefied that surface pressure is about 1/1000th of Earth's, comparable to the best laboratory vacuum achievable here on the ground. That means you can't count on effective parachutes like the ones used on Mars or Titan. The atmosphere is far too thin to provide any meaningful aerodynamic braking during descent. You have to carry essentially all the delta V needed for a propulsive landing. Every meter per second of speed you need to shed has to come from fuel you brought from home. More mass, more complexity, more potential failure points. It's no surprise then that to this day, no mission has ever seriously attempted a landing on Io. The list of probes that have approached the moon is short and tells a story of hard-nosed engineering caution. Voyager 1 and 2 made close flybys in 1979, revealing active volcanism for the first time. One of the most surprising discoveries of the space age, since nobody had expected to find active volcanoes on a moon. Galileo made several close flybys between 1995 and 2003, collecting invaluable data but at the cost of accelerated aging of its electronic systems. New Horizons in 2007, on its way to Pluto, used Jupiter's gravity for a slingshot assist and photographed Io in passing. Juno, the probe that has been studying Jupiter since 2016, only recently approached Io carefully, planning each pass to minimize exposure to the most intense radiation and not jeopardize the primary mission. Nobody has dared to go down. And yet people are seriously thinking about it. NASA has proposed a mission called the Io Volcano Observer, or IVO, which could launch toward the end of this decade. Not a lander, at least not yet. A dedicated Io orbiter designed specifically to withstand Jovian radiation, better than any probe before it. The challenge is enormous, but not impossible. Radiation shielding technology has improved enormously over the past 20 years, and designers can draw on lessons learned from Galileo and Juno. IVO would perform dozens of close flybys collecting data on volcanic composition, internal structure, and the rate of heat generated by tidal heating. It will be an important step, but the real feat, an actual lander, still belongs to future generations. So, here's the final answer. If the question is which combination of orbital difficulty, geological violence, unpredictable terrain, and radiation environment makes a landing a near-perfect nightmare, then Io takes the podium without breaking a sweat. Not because it's truly unreachable, but because every single aspect of its environment seems designed by a sadistic engineer to make your life as complicated as possible, in the most creative ways imaginable. Today we know that this small yellow-orange moon, yellow from sulfur, orange from frozen sulfur dioxide, streaked with black from fresh lava flows, is the most alive and most violent place in the solar system. Understanding what it truly means to land there will only happen when someone, someday, has the courage and the technology to actually try. So what do you think? Did watching this video raise any doubts or questions? If so, please let us know in the comments. And if you want to explore more impossible journeys, check out our How Long to Reach series, where we break down the travel time and challenges of reaching other worlds in our solar system. How long to reach Mars, Saturn, and the edge of the solar system. Click the links on screen to continue the journey.